Welcome to 51st lecture in the course of Industrial Engineering and Operations Research. We are discussing operations research. We have discussed many interesting topics: linear programming, transportation model, part and CPM, and now today I am going to discuss about queuing theory, which is an important subject. Even in the computer science also they study queuing theory. It is concerned with the waiting line models. Suppose you go to railway station and you want to purchase ticket from a counter, you will see that there is a queue, and in that queue you have to stand, and so therefore what theory will do? Theory will estimate that what will be the queue length on an average, whether I should open one counter or two counters, these type of things will come. So probability is an integral part of the queuing theory. Why probability? Because if everything is deterministic, then perhaps there will not be even any queue. Suppose a doctor takes exactly 10 minutes to see a patient, then everybody's time can be assigned. That means in 1 hour he can see exactly 6 patients, and they can come on the exact time. Suppose one patient come at 10 p.m., other can come at 10 p.m. like that. Then another one can come at the end of 10:20 p.m. and then they can get the checkup and they can go. But usually this doesn't happen. Although the doctor takes 10 minutes, but you know that sometimes it may be even less than 10 minutes, sometimes it is more than 10 minutes. So there is some probability distribution. So therefore it is possible that sometimes even a person knows that there are 3 patients before me, but he may go and find that still the doctor is engaged in talking with the patient. So naturally the queue time will be there will be some queue length. Okay, some people have to wait. Okay, so this that's why probability is an integral part, and we talk things on an average, and we do that. So queuing theory is a branch of operations research that studies how waiting lines form, how they function, and why they malfunction. So we have to say that waiting lines, that means there will be say some suppose there is a counter here and this is counter, and then people are going maybe that, and they are standing. Okay, they are standing in the queue and they are going like that to that counter. So how they form? Naturally, that that if there is a probability in the service time, and even customers come also in random manner, how they function and why they malfunction, that means sometimes too much waiting time or something. So word line doesn't only mean a physical line of people. Sometimes you see that people stand in the line, but it refers more broadly to any situations where customers, that means customers may be people, it may be data, it may be jobs, wait for service. So it may be scooters waiting for the servicing, it may be the even the computer, suppose it is doing some job and jobs keep waiting in the queue. Any type of thing can be there. Origin of queuing theory can be traced to the early 1900 means after something, basically you can say 20th century, in a study of the Copenhagen city in Denmark telephone exchange by Agner Krupp Erlang, a Danish engineer, statistician and mathematician. Agner Krupp Erlang, basically we say Erlang, he was engineer and also very strong in statistics and mathematics. So he did some work related to telephone exchange, that how you have to wait In those days, people have to wait a lot for cars also. Trunk car system was there. People are waiting, and the time will come, then they will do that, because at one time there cannot be cars at several places. So he just analyzed the situation by means of his statistics. Queuing theory studies behavior of waiting lines, that is queues. It examines every component of waiting lines. So waiting line and queue is basically the same term, including, so there is a arrival process and then the number of customers among others, and this is what. So it models arrival, then service, how the service is done, then waiting and how the entities depart. It uses probability and mathematical tools. Basically, it uses the probability. Queuing theory aims to achieve a balance that is efficient and affordable. Balance means in what sense? That suppose I have to open 2 counters or 3 counters, so that people don't have to wait. You might have seen at the airport, when you go that, the security personnel are standing here in parallel type of rows, and customers, that passengers, they go this side, and if this queue is long, then they go here, then they go here, and sometimes suddenly people see that there is a lot of crowd, then one more counter is suddenly opened, and sometimes that counter is closed also. That type of situation you might have seen also. So it basically if you open more counter, that means more expense. Suppose you are having 4 counters, so there are 4 security persons you have to employ, and they have to be present there. That cost of their salary etc. has to be paid, but waiting time will get reduced. If you employ only 1 person, then it is a cheaper alternative, but then customers will have to wait a lot and they will get dissatisfied, and that cost will come. So you have to make a balance, that how many counters should be opened, what is the optimum way. Used as an operations management tool, queuing theory can address scheduling and customer service shortfalls. So it can be useful in scheduling and customer service. What are the shortfalls in the customer service? At a basic level, queuing theory involves the analysis of arrivals at a facility, such as a bank or a fast food restaurant. So it analyzes the processes currently in place to serve them. What is the present system? How much is that? So we can give many real life examples of queues. Say for example, in petrol pump, you have already seen, you must most of you have that experience, that when you go for filling the petrol or diesel in your vehicle, maybe car or scooter, you have to wait. There is a service facility, that means fuel dispenser thing is a service facility, and many petrol pumps, there are 4 dispensers. Some places there will be 2 only, so that parallelly that at one counter the fuel is getting filled, and another counter also it is there. Similarly, hospital also, customers are patients and service facilities doctors. Suppose I have gone to various hospitals, their general physicians are sitting. So suppose there are 4 chambers and doctors, and at the reception they give the token number and name of the doctor. So you have to wait. You can go, you can go here, or you can go here, or you can go here. So it is basically multi-channel type of thing. Nurses also, they are also limited. Beds are also limited, so you have to wait. In job interview, when the candidates are called for job interview, then candidates wait, and there are some interviewers. In railway station, travelers go, and there are ticket counters. And even what we can say, that when we book the tickets in the train, then we get a waiting line or something. That is also, so we can say in entire train also there is a waiting line concept. In the train, how many berths I should be having depending on my statistical data. In the cars have to wait for the washing facility, okay, and then mechanic also may be limited. So, these are the examples, and how we arrange the arrangement of service facility. You see that there can be a service facility like here, but this is only one counter. It is called single queue, single facility. That means one queue is there and one facility is there. So, these are the queues of customers. At the moment you are seeing that 3 customers are waiting here, and this is the service facility. But you can have a situation that the queue is only one, there are 3 persons in this one, but once you reach that spot, then there are basically 2 service facilities, service facility 1 and service facility 2. So, you can say single queue, but you can have multiple facility. Modeling of both the cases will be somewhat different. Okay. There can be another type of arrangement, there can be multiple queues and there can be multiple facilities. Okay. So, you can have service facility 1, service facility queue. So, each one service facility, one queue, separate queues are there, Q1, Q2, Q3. So, multiple queues and multiple facilities. So, many type of things are possible here, single queue, but multiple facility. So, main players in a queuing situation are customer and server. Okay, they are the main thing. Customers arrive at the service, which is called facility also, from a source. Some source is there from where people are coming. On arrival, the service may start immediately, or the customers may wait in a queue if the facility is busy. So, that means these type of situations may be there. And when the service is completed, it pulls a waiting customer from the queue. If the queue is empty, the facility becomes idle until a new customer arrives. So, this is also the thing that if you open too many facilities, then some may be idle also. If in a hospital there are 10 doctors and both are, every doctor is basically general physician, then some of them may be waiting. So, arrival of customer is represented by inter-arrival time, that is called inter-arrival time, time between successive arrivals, that is has to be known on an average sense, and maybe should be known what will be the distribution. Suppose I say that inter-arrival time is 10 minutes, that does not mean that exactly at 10 minutes someone will come. It may be sometimes more and sometimes it can be less also. So, queue discipline represents the order in which customers are selected from a queue. Common disciplines are FIFO, LIFO and CILO. That this discipline means some system has to be followed, like it can be first in first out. That means first item or person to enter a system is the first one to be processed or served. Example is that if you give many jobs in a printer, then the first document sent to the printer gets printed before the next one. There is a queue, and then queues at a ticket counter. The person who arrives first gets served first. That is always there. Inventory management, the oldest stock first in is sold or used first in grocery stores to avoid spoilage. That is also there. If you go to a fruit shop, the fruit man will try to sell you old mangoes first, and then after that only he will take out the new stock. So, there also it is first in first out. That means mango which came first, that goes out also first. But last in first out system is also used sometimes. Last item to enter is the first one to leave. Example is that in a software, if you see undo function, then last action is the first to be undone. Suppose you are typing and you by mistake you wrote the wrong spelling, then you undo it, it goes deleted. Again you do undo, then the previous word also get deleted, like that it happens. Stack of plates, if we put a plate in this one, like in sometimes in buffet system, in marriage, etc., we go and we stack the plates. So, last plate is taken first. Okay. Then browser history or call logs. The last site we visited or call we made appears first. But it can be service in random order also. It refers to a queuing discipline where customer of items are served in no specific order, but rather randomly selected from the queue. Examples are that resource allocation during emergencies. When order is not critical, resources might be distributed randomly, like relief kits in some disaster zone, like whoever is coming that you just give. Lottery based prize distribution, tickets are drawn at random and prize winner is declared. So, these situations can also be there, and analysis of these will be different in terms of the waiting time for the customer. Then we just discussed that if we make, I am discussing all these details, but it does not mean that we will be tackling with all those things, so many difficulties, but we will make some simplified model first, then slightly more complicated like that, and maybe we will view at just at slightly more complicated level, but you know that queuing theory also can be a separate subject. There are books which are totally devoted to queuing theory, and it can be actually one semester course also. So, therefore, idea is that I am just introducing so that you can study those things in detail if the need be there. So, let us discuss about queuing behavior. In the queuing behavior, there is term called jockeying. Jockeying means switching queues. To reduce waiting time, customers may jockey from a longer queue to a shorter one to reduce waiting time. For example, at toll booths, drivers often change lanes hoping to get through faster. Even I have gone at airport and I saw that I did this type of situation. These are the queues. Okay, security check. That security man is standing at this spot, that is square spot, and suppose I am seeing that here all people. Okay, so suppose I am standing here. Let us say this is me. And then I saw here, this is like this is suddenly that that this fellow was fast, so it went, and so I saw, okay, there is only one person in front of, there is only one person in the waiting line, but here two, so let me go from here to here, so I jump. So, this is called jockeying. So, I jockey it from one place to other place. Balking means refusing to join. Sometimes when we see too much crowd, customers can balk from joining a queue altogether because of anticipated long delay. For example, at a restaurant, seeing a long waiting line, someone might decide not to wait and leave. Sometimes we go to restaurant with the friends and we say, chal yaar, we have to go to other place, it is very crowded, and we go to another one. Okay, so this type of thing is also done, that is called balking, because there is a queue but we refuse to join. Another behavior is called reneging, that means leaving after joining. Customers may renege from a queue because they have been waiting too long. For example, in a bank I went, we took the token, but it took long time, then we came. Even at the doctor's clinic we sat for many hours and he is not giving time, then we just go away. So, this is many times we sit in the restaurant and we see that the service is very taking much time, then we run away. And now coming to the elements of a queuing model. Okay. So, the source from which customers are generated may be finite or infinite. Infinite source example is that number of potential customers is very large or unlimited, sometimes almost infinite. Hence, the arrival of one customer does not affect the chances of other arriving. For example, calls keep arriving at a telephone exchange one after the other. But the finite source can be total number of potential customers is limited. When one enters the system, it reduces the number of potential arrivals temporarily. For example, suppose the machine shop has about 10 machines and 3 are being repaired, then only 7 machines can enter the queue. Okay, there is nothing. So this is a finite source. Okay. Role of exponential distribution in queuing theory. So very important thing is exponential distribution. It has been done by study. It has been done by that behavioral scientists, that in most queuing situations arrivals occur randomly, and random means that the occurrence of an event, that arrival of customer or completion of a service is not influenced by the length of the time that has elapsed since the occurrence of last event. Okay. So suppose you are sitting at doctor's chamber, you went at about something like that at 4 p.m. then how much chances are there that by 4:30 another patient will come? That is not dependent on your behavior, it is totally random. So random inter-arrival and service times are described quantitatively in queuing model by exponential distribution. Suppose there is a randomness in this one time, then this is described by exponential distribution. It can be shown mathematically, it has mathematical basis. That why do we say exponential distribution? That means arrival is random. So exponential distribution means if the number of arrivals at a service facility during a specified time period follows the Poisson distribution, we say then the distribution of inter-arrival time is the negative exponential or exponential distribution. So what I am telling, that this also can be shown mathematically. That means if there is a Poisson distribution is there in arrival, then the service time will be exponential. So if lambda is the rate of arrival, then the probability density function of inter-arrival time is this one. This is a inter-arrival time x is this, fx is equal to lambda e minus lambda x exponential minus lambda x. Lambda is the rate of arrival on an average and x is of course greater than 0. This is called probability density function. I hope you know the probability density function. Difference in the probability and probability density function is like this, that if you want to find out that in the time interval delta x, how much will be the probability that something will happen in the time interval delta x, then that probability is done by fx delta x. That means product of this and this gives you the probability. Fx is not giving any type of probability. In fact, in this case you see that fx has got a unit of per second. Okay, if x is in second, so this is fx has got a unit in per second, second inverse. So you multiply it by second, then it becomes non-dimensional, because probability has to be non-dimensional. You see e minus lambda x will be non-dimensional because it is this one, and lambda is this is lambda is basically a arrival rate, and this is how that this relation. So that means we what is the meaning of this, that here if I take 0 to infinity and I say fx dx, that will equal to 1. Why? Because fx dx, if I add small probabilities, then their summation will be 1. In a delta x interval, what is the probability? Fx delta x. So summation is represented by integration. So 0 to infinity fx dx should be equal to 1. You can verify if you integrate lambda e minus lambda x between 0 to infinity, the result will be 1. And graphically also we can show that. Here we can say fx and here x time we can plot, and we can have some type of this thing like this type of curve. Okay, here from here it can go like exponential way. So that means naturally that density. So you know that if I want to show, you see density function keeps decreasing, that means, but if I want to find out that what is the probability of occurrence of this event between this time to this time, that you can take area under the curve. So, if I find out the mean and variance of exponential distribution, mean is basically Ex is equal to 1 by lambda. What do we mean by mean? That as we have said that this is f x lambda e minus x. So, this is a probability density function. If you multiply it by f x f x, so if you say 0 to infinity x f x dx, that will give you mean. Okay. And similarly, the variance come out to be 1 by lambda square. So, therefore, mean, that means mean time of arrival is basically 1 by lambda, which is sometimes you may look you to obvious that suppose there are 10 arrivals per minute, and if I ask you that what is the mean, okay, so mean will be basically that suppose lambda is equal to 10 customers per minute. So, therefore, you can have 1 by 10. So, 1 by 10 will be 1 by 10 minute is the mean of the inter-arrival time. That means, you can say in 1 by 10 minute one customer comes, which is obvious, but you know if you it can come mathematically from there, and variance is 1 by lambda square. Standard deviation is square root of variance. So, standard deviation is also 1 by lambda. So, therefore, the mean Ex is consistent with the definition of lambda. The lambda is the rate at which event occurs, at which events occur, and therefore, 1 by lambda is the average time interval between successive event. So, anyway, I will just tell some derivation also. Key difference between Poisson and exponential distribution. Poisson distribution is very much related. So, Poisson distribution tells number of events in time, that suppose I give time interval 1 hour. So, in 1 hour interval, what is the probability that 3 persons will come, what is the probability that 4 persons will come. So, it is discrete, and in exponential distribution it is basically time between events. Example, a customer care issues car randomly, the average inter-arrival time is 3 minutes. So, what is the probability that inter-arrival time does not exceed 2 minutes? Okay. So, average inter-arrival time is 3 minutes. So, determining the probability is same as computing the cumulative distribution function of x, that cumulative distribution. Cumulative means up to this how much. So, that means we say up to, suppose x will be smaller or equal to t. What is that probability? That this is 0 to t lambda e minus x, because lambda e minus lambda x is the distribution. So, it is 0 to x. So, probability that it will be less than this one will be this. If you integrate, this becomes minus e minus lambda x, and limit is 0 to t, and then it becomes 1 minus lambda t. So, that means probability that x will be smaller or equal to t is how much? 1 minus e lambda t. Probability that x will be smaller than 0, smaller or equal to 0, what is the probability? That it is 1 minus e to the power minus 0. So, that means e to that 1 e minus 0 is 1. So, this is 0. So, naturally 0, because nothing can be less than 0 and exactly at 0 also, but probability that x is smaller or equal to infinity, naturally it will be 1 minus e to the power minus infinity, because and this becomes e minus infinity 0. So, this is 1. So, it has to be this one. So, in between it is like this. So, arrival rate is lambda is equal to 1 by 3 arrival per minute, because this was given 3 customers. Average inter-arrival time is 3 minutes. So, therefore, lambda is equal to 1 by 3, and substituting t is equal to 2, because we are asking that the probability that inter-arrival time does not exceed 2 minutes. So, substituting t is equal to 2, that means probability that x will be smaller than 2 is 1 minus e to the power minus lambda, that means minus 1 by 3 into t, and if you solve it, it will be 0.487. So, we will discuss little bit more on probability distribution. Suppose fx is equal to lambda e to the power minus lambda x, x greater than 0. The probability of x lying between 0 and infinity is 1. This is true because 0 to infinity fx dx is equal to 0 infinity lambda e minus x dx is equal to this much, and this is equal to basically this one. If you integrate this integration will come here this, and 0 to infinity, that is basically 1. E to the power 0 is 1 and e to the power minus infinity 0, you remember that. Expected value, which is mean is of any exponential distribution, is what? Expected value of a continuous random variable is given by Ex is equal to x fx into dx. So, basically we are giving x multiplied by the probability. Probability is fx dx. Since fx is equal to 0 for x is smaller than in 0, we can integrate from 0 to infinity. So, expected value of that variable is 0 to infinity x lambda e minus x dx, and this becomes Ex is equal to minus x e to the power minus lambda x 0 to infinity plus 0 to infinity e minus lambda x dx. By taking the first and second function method product rule, we have written this expression. You can see this, you can pause your video, understand that type of thing. And then Ex is equal to 0. So, this limit, if I put that minus x e minus lambda x 0 to infinity, naturally it will come out to be 0. If I put even infinity, so this moves faster and this moves slower. So, this entire thing will be 0, and you will get 0 to infinity e minus lambda x dx. This will be minus 1 by lambda e minus lambda x, and limit is 0 to infinity. This becomes 0 plus 1 by lambda. So, expected value of the inter-arrival time is 1 by lambda, okay, which is obvious. Variance is that 0 to infinity x minus x bar, how that is differing from the mean. So, you have to say x minus x bar is square, and you have to say fx dx, and you put 0 to infinity. X minus x bar is 1 by lambda because that is the average value. X minus 1 by lambda is square multiplied by fx. Fx is lambda e minus lambda x dx, and you expand this. This becomes x square minus 2x by lambda plus 1 by lambda square into lambda e minus lambda x dx, and you now have written 3 integrals. This is 1 integral, this is 1 integral, this is 1 integral. So, you have to integrate all these. This integration is very easy, last one, because e minus lambda x integration will be e minus lambda divided by minus lambda, and here you have to use product rule. Here you have to use product rule 2 times, first function second function concept, but if you do that, then variance of x will be lambda. This will be 2 by lambda cube, this is minus 2 by lambda 1 by lambda square, 1 by lambda square lambda, and this whole thing you do that, this becomes 1 by lambda square. So, this is how the variance is 1 by lambda square, and standard deviation is 1 by lambda because this is the type of this one. So, only this much today you have understood about the queuing system behavior, and you also have understood that basically inter-arrival time is usually assumed to follow exponential distribution, and what are the properties of the exponential distribution. Thank you very much. Okay.